Now we start the study of some interesting, given a graph, of some interesting subsets of the sets of vertices or edges. And in particular, we're going now to study matchings. No, not here. Here. Coverings. This we study today, but then we have their counterparts, edge coverings. Independent set. And there is also a click. But for today, we are just to study matchings and coverings. Matchings are some particular edge sets as much as edge coverings, whereas coverings and independent sets and clicks are sets of vertices. Okay? All right. We have a graph G, we have its edge set E, a subset M of E is called a matching if its elements are links, so no loops, and no two of them are adjacent in G, meaning that the two, they have no vertex in common, okay? The idea of matching is to match vertices through this, meaning to take them by pairs, okay? And so if you find some edges, okay, this means take one edge, take the pair of its ends, another edge not adjacent, another pair of vertices, and so on and so forth, okay? A single edge, a single link of G is by itself a matching, okay? Because it is a set of edges, no two of which are adjacent. There is just one, and so, okay. All right. Of course, we are interested in rather big matchings, okay? Not just one edge by itself, okay? The two ends of an edge in M, so now M is such a set of edges, a matching. The two ends of an edge in M are said to be matched under M. A matching M is said to saturate a vertex V, and V is said to be M saturated, if some edge of M is incident with V, okay? Otherwise, V is M unsaturated. If every vertex of G is M saturated, the matching M is said to be perfect. Be careful now, M is a maximum matching if G has no matching M prime with cardinality of M prime greater than cardinality of M. Number of elements of M prime greater than the number of elements of M. Okay? Of course, if you have a perfect matching, this is maximum, meaning it saturates all vertices, and so there is no possible vertex, no possible edge to be added, and so it is the maximum. Actually, if you have a perfect matching, then how many edges are in a perfect matching? The number of vertices divided by 2. Okay, and so there is no possibility of having more than that in a matching. So a perfect matching surely is maximum. Let me add something to this part, which is talking about maximal matchings, okay? What do I mean by a maximal matching? I mean a matching such that if you add any edge to it, it is no more a matching. More than here, it is here, maybe that I can give you this idea. Here, I'll repeat this on my board, okay? Okay, let's see what, here we have a perfect one, so there is no, no, this is no good example, I'm sorry. The better one is then, sorry, I should not do improvisations. This is useful for coverings, but let's go. Now, let's go to this, and so. Okay, they show you here maximum matching, which is this. Okay, this is a maximum matching in the sense that you can try with brute force. This is very little, so you can do brute force on it and try any other possible matching. Okay, you can easily find another one by taking these two edges instead of these two, okay? And then you get another matching, but still it has 3 edges, okay? And you can find other matchings which will have less than 3 edges, possibly, okay? For instance, look at this. If I take this edge and this edge, is that a matching? Sure it is, okay? Here are these two red edges which have no vertex in common, okay? Is that a maximum matching? No. Why? Because we know that there is the green one which has 3 while this has two edges, okay? So it's not a maximum one. But it is a maximal matching. What do I mean? I mean, if you try to add any other edge, then you get no more a matching. Sorry, should do it here, maybe. Okay, let me do it again here. If I take this and this, it is surely matching. Okay, let's try to add in yellow an edge. I add this. Is it a matching? No, because they have these two have a vertex in common. Okay. I tried adding this. Is this a matching? No, because they have a vertex in common. I add this. No, because they have a vertex in common. Okay. This no, because they have a vertex in common. This no, because they have a vertex in common. So this is a matching, and it is maximal in the sense that there is no matching containing it properly. Okay? So you can have a maximal matching, which is not a maximum matching. If you have a maximum matching, it surely is maximal. Okay? And if you have a perfect matching, it surely is maximum, and surely it is also maximal. All right? And okay, but the book does not talk about maximal matching. Still, it is important to have this idea of maximal something inside the graph or inside anything. Okay. Sure. Just a moment that I have to add this. Okay. Let me say here. The green matching is maximum, but not perfect. So it is also maximal. The red matching is maximal, that is, there is no matching. Let me say no bigger matching containing it, but not maximum. Okay? All right? Okay. So, this graph here cannot have a perfect matching. Why? Because of these two edges and three vertices here. Okay. I mean, if you want to saturate this vertex, you must take in this edge. Okay, and it is actually possible. No problem in putting this in a matching. Okay, let's do it. Okay. I can put this. Oh, I can put this in a matching, okay, and I can have, for instance, this, and why not this? So it can go in a matching, and this, you see, is the matching because these blue edges do not have vertices in common. They are not adjacent with each other. And it is a maximum matching because it has three edges, as many as the green one here. But you can never have a perfect matching here because if you want to saturate this vertex, you need to take this edge. And so you saturate also this vertex. But then you cannot saturate this other vertex because you would need also this edge, and this is impossible because then they would have a vertex in common. Okay? So this is surely, here it is surely impossible to have a perfect matching. Can you tell me in 10 seconds another situation in which you surely cannot have a perfect matching? A graph? 1, 2. Hmm? Bygone? Sorry, without math. A cycle? No, not necessarily. Not necessarily. I'll give you examples. I like that you do like this. I give you examples for what you're saying. Here is a cycle which has a perfect matching. And here is a tree which has a perfect matching. Oh, sorry. Something for which you can say, no, this surely has. You look at it and this cannot have a perfect matching. No. You will laugh when I tell you the answer. If it has an odd number of vertices, of course, it cannot have a perfect matching, because a perfect matching would mean that by certain k edges, I cover all 2k vertices. But if the vertices are an odd number, then it is impossible. Let's modify your example, that is, make particular examples of your classes. Who said the cycle? Sorry, you, and they didn't. Okay. Here is a cycle which has no perfect matching, and here is a tree which has no perfect matching. Okay, and any graph with an odd number of vertices, of course, cannot have a perfect matching. But be careful, because again, this is a one-way implication. This cannot have a perfect matching, but it has 1, 2, 3, 4, 5, 6, 7, 8, and an even number of vertices, and so having an even number of vertices is a necessary but absolutely not sufficient condition for a perfect matching to exist. Okay? So now we are more familiar with this idea of matching, perfect matching, maximum matching, and also something which is not in the book, maximal matching, I hope. Okay. So we are interested in the presence of perfect matchings, but that is more tricky. Let's think of maximum matching at least. Okay. So now we have a theorem talking about existence, whether a matching is maximum or not. So here, let M be a matching in G. An M alternating path in G is a path whose edges are alternately in M and its complement, M and its complement, M and its complement. And you can see this V5, V8, V1, V7, V6 in the graph of figure 5.1a. So let me see what is here. V5, V8 is not in the matching, V8, V1 is in the matching, V1, V7 is not in the matching, and V7, V6 is in the matching. This is an M alternating path given this particular matching M. Okay? What is an M augmenting path? Is an M alternating path whose origin and terminus are M unsaturated. Okay? Let's see in my example. This is a matching, okay? And we can have an M augmenting path, which is this, for instance. I start here, not in the matching, in the matching, not in the matching, in the matching, not in the matching. Okay, so this is M alternating and also M augmenting. Why? Because it starts and ends with edges which are not in the matching. This is an M augmenting path. Theorem, a matching M is a maximum matching if and only if G contains no M augmenting path. So this is something which proves immediately that this matching is surely not maximum. Okay, and you can imagine how it can be that we can see at least one way of the proof. I'm not giving you the proof, but the idea is just reverse the matching inside the M augmenting path. And so you get exactly this green one, okay? And so you switch between M and non-M. So you put in M prime, the edges which are here not in M, and conversely you take this away. So you put this, take out, put, take out, put, and necessarily you have one more edge in the new matching, okay? And you get actually exactly the green one if you do like this with this particular M augmenting path. But this is a part of the proof, and I do not give you the proof. Anyway, you have an idea for seeing when matching is or is not a maximum, because you can check that it contains no M-augmenting path. Show that every K cube has perfect matching. Do that, okay? In which way, again, you have to reason on the general K cube, and of course you can start with the normal cubes of little k, which you can draw easily, okay? You start with them, you work out something which should be general. So if I give you a 1000 cube, you must tell me how to produce a matching inside it. Okay, perfect matching inside it. And show that that's tricky, no more than 10 minutes for that. Show that the tree has at most one perfect matching. It cannot have two. Then there is this, which is tied with the ideal K factor, but so I'll skip it for the moment. I want to cover the propositions which are in this chapter. An important part of the theory of matchings is when we have a bipartite graph, okay? We'll see an application of matchings for a bipartite graph. For any set S of vertices, we define the neighbor set of S in G to be the set of all vertices adjacent to vertices in S, okay, and denote it by NG of S. Suppose that we have a bipartite graph with bipartition X and Y. And sometimes it is, you build the bipartite graph exactly to find the matching that saturates every vertex in X. One example is the personal assignment problem, the application I was just mentioning. Now, does such a matching exist? We have a theorem by Hall, which is this. Let G be a bipartite graph with bipartition X and Y, then G contains a matching that saturates every vertex in X, if and only if this thing happens. Take any possible subset S of one of this set of the bipartition, the one you want to saturate, okay? Any subset of X. Then you must check that the number of vertices in the neighborhood of S has at least as many vertices as S itself, okay? This is an if and only if situation, a necessary and sufficient condition, okay? So you can use it not only for negative answers, but also for positive answers. Also no proof for this. Corollary, if G is a K-regular bipartite graph with K greater than 0, then G has necessarily perfect matching. So K-regular means that it's not complete bipartite graph. No, it just means it is bipartite and you have the same degree for all vertices of X and of Y. If you have a K-regular bipartite graph, then out of the previous theorem, you can get that G has a perfect matching. And this is known as the Marriott's theorem. And you can state it like this. If you have a village, all of heterosexuals, okay, and every girl knows, not in the biblical sense, just in the social sense, knows exactly K boys, and every boy knows exactly K girls, then each girl can marry a boy she knows, each boy can marry a girl he knows. Okay, there is surely a matching out of this graph that you can build, because it means that your bipartite graph is actually K-regular. K for each of the vertices, degree K for each of the vertices of the girls set, K for the degree of each vertex of the Boy's set. Okay? All right? Now we switch to the other type of sets I mentioned. We had talked about matchings. We are going to talk about coverings. What is a covering of a graph? A covering of a graph G is a subset K of V this time, such that every edge of G has at least one end in K. Okay? A covering K, so think of this. Is it easier to build a small or a big matching? A small one. Just one edge, matching. I'm aiming generally to a matching which is as big as possible. Okay? So you are interested in maximum matchings, maximal matchings, and so on. Coverings. Can you build a covering of a graph? Here, you know, every mathematician would have jumped to say, yes, I have one. Take all of V. Okay? If I want a covering of G, such so a subset of V, such that every edge has at least one end in K, okay, take all of V. Mathematicians are very happy with this answer. Of course, engineers are not. Why? Because engineers always think not just of the definition, but of the hidden aim of that definition. And the hidden idea of the definition of covering is that you want a small covering. So taking all of V is stupid, but perfectly adhering to the definition. But the idea is I want a small covering. Okay? And here is a possible reason why I want a small covering. My graph is the graph of painting exhibition. Okay? Paintings are generally, well, you might have big rooms, but generally they are on the corridors themselves, okay? And you want to put there guardians, okay? And so what has a guardian to do? To be at the vertex in order to check several corridors, okay? Of course you can put a guardian at each vertex, but you pay quite a lot. This is evident to an engineer, meaningless for mathematicians, because mathematicians do not know very well the notion of money, okay? Engineers do, of course. Okay, so you want to pay as few guardians as possible, but you do not want to leave a corridor unchecked. Okay, so you want a covering and possibly a minimum covering, meaning as few vertices covered as occupied as possible. Okay, so minimum covering such that there is no covering K prime with less vertices than K itself. Okay, and look at this here, for instance. You have this covering. Of course, if you put your guardians here, all corridors or edges are checked. Okay, but if you are smarter, you put them here. Still, you are checking all corridors. Okay, but you pay 4 people instead of 5. And again, look, this is a covering. It is not a minimum covering, but it is a minimal covering. okay? In the sense that if you have set your guards here, if you take one away, then there are corridors which are not checked exactly one. But this is what you do not want to have, okay? And so it's not minimum, but it is minimal. There is no smaller covering contained in it. Okay. If it is minimum, of course it is also minimal. But you might have a minimal one which is not minimum, as in this case. Okay. Sorry, where is it? Okay. Now, let's compare what happens if we have in the same graph a covering and the matching. Okay? A covering, so all edges have at least one end in the covering. Okay? By definition. M, a matching. So no two edges of M have a common vertex. Okay? Then K, the covering, contains at least one end of each of the edges, okay, of M. Do you see what I mean? If you have, so let's go now here. Let's take okay, not the minimum one, this one, okay? And let's take a matching, say this one. Okay, so every edge of the graph has at least one end in a red vertex, okay, because the red vertices form a covering. All right? So now we can do this. We can, so if you take in particular the edges of the matching, of course, either one or both the ends of that edge belong to the covering. In this case, both. In this case, both. In this case, just one. So now, what I can do what? I can decide for every edge of the covering to assign to that edge one vertex of the covering. So to each edge of the matching, I can assign one vertex of the covering. In this case, for instance, I have just one of the in the covering. To this edge, I assign this. To this edge, I could assign either this or this. Decide, flip your coin, okay? You flip a coin and decide to this edge, I assign this. Flip a coin for this edge, which has both ends in the covering, and you decide this, okay? So you can have what? An injective application from the set of edges in the matching to the set of vertices in the covering. An injective application, okay? This tells us what? That the number of edges in the matching is less than or equal to the number of vertices in the covering, okay? You see what I mean? Since you can, do you remember we talked about that when we had the problem, the pigeonhole principle, okay? If you can have, what does it mean that a certain number is less than or equal to another number? It means that if you take a set with the first number of elements and the set with the second number of elements, you can have an injective application from the first set to the second. Okay, so since I can make an injective application from the set of edges of the matching to the set of vertices of the covering, then surely the number of for any matching M, any covering K, the number of edges in M is less than or equal to the number of vertices in K. And even we can have this. If M star is a maximum matching and K tilde is a minimum covering, then in particular, we can have this. We have this, that the set, it is a particular case of this. The number of elements in M star, maximum matching, is less than or equal to the number of vertices in K tilde, minimum covering. Okay, let's take this other. This other, oh no, let's take this minimum covering. Okay, and the matching was all right because it was a perfect matching, so it's also a maximum matching. Okay, so I have this, and I have this. Now, this edge necessarily points to this vertex. This edge necessarily to this vertex. This edge either points to this or to this. Flip a coin and decide. And then you have, again, of course, an injection from the set of edges of this, which is a maximum covering, to the set of vertices of this, which is a minimum, which is a maximum matching to the set of vertices of this yellow, which is a minimum covering, which is a particular case of the general rule. Here we have this, okay? But, okay, in general you have this, that you never overcome with the number, even of a maximum matching, you never overcome the number of vertices of even a minimum covering. In particular, Koenig's theorem, let M be a matching and K be a covering. The theorem is here, okay, and we have also this lemma to this theorem. Let M be a matching, K be a covering such that they have the same number of elements. Then M is necessarily a maximum matching and K is necessarily a minimum covering, okay? M, this is nice to know by itself, but it is also what is needed to show this, which is Koenig's theorem. In a bipartite graph, the number of edges in a maximum matching is equal to the number of vertices in a minimum covering. Okay? You do not have the less than. For bipartite graphs, for a maximum matching and the minimum covering, you necessarily have equality. Okay? Of course, this which we used is not a bipartite graph, and so we have a strict inequality between 3, which is the number of edges of this maximum matching, and 4, which is the number of vertices of this minimum covering. Okay, but you can check, build your preferred bipartite graphs and check that the numbers will be equal, okay? And so we have this first relation of interest for us, which is this G for G bipartite. Number of maximum matching equals number of minimum covering. Okay? General, you have less than or equal to. Okay? quite a lot of interesting things which we skip. Let's go to the application and then we go back to factors. I have time to go back to that exercise, which we will just consider for a little part. Personal assignment problem. You have a company and workers, x1, x2, xn, and n possible jobs, okay? But you have that, it's not a complete bipartite. It is a bipartite graph, the one in which you connect a worker to the jobs he or she is qualified for, okay? But in general, it is not a complete bipartite. It may not be true that you have that all workers of that company can do all jobs, okay? Probably, hopefully, each one of these workers can do one or more than one job, at least one. If we are not in Italy, where you can have a recommended person who does not know what to do, but he's paid anyway. You must know what the problems in Italy are. You have also this type of problems. Okay? A worker of degree 0. He does not know what to do, but we pay him or her all the same because he's the nephew of a very important political person. Okay. You have the same. Okay. Okay. So some graph theoretical problems also in Turkey. Okay. All right. And hopefully you also do not have any job of degree 0, meaning that for every job we have there is at least one worker able to do that job, and hopefully more than one. Okay. Now, you want to assign each time, of course, a person has to work at one job at a time. Okay, and so what you actually want is a matching. All right, and a matching which saturates what? Possibly everything. So every worker is assigned to a job, and every job is saturated by this matching. Okay, but anyway, you know what's your priority. Maybe you need that in that moment all jobs are actually performed, okay? Or maybe you do not have this problem, but you do not want to pay a worker to do nothing, okay? So you construct the bipartite graph, and then is there or not a perfect matching? And you know that this is possible to have such a matching according to Hall's theorem. You look for any set of workers, whether its number is greater than or equal to or not the number of jobs in its neighborhood, and so you can know whether you can actually determine a perfect matching. Okay? Okay. So you can, my intention is to say, you can model in this theory this problem. Okay? Let's go back to a generalization of matchings that we touch only in this case, only for very little things. What is a K factor of a given graph G? It is a K regular spanning subgraph of G. Okay. So, what is a perfect matching in this? Why do I say that this idea of K factor is a generalization? Because it generalizes the idea of perfect matching. A perfect matching is nothing but a one factor, meaning if you have a perfect matching, it means what? That you have that the edges of the perfect matching together with their ends form a spanning subgraph, okay? And actually, in this subgraph, every vertex has degree exactly 1. Okay, so it is a one factor. If you have a perfect matching, this enters in this definition with k equal to 1. Okay. And so here I forget about all what they ask you to see and to learn. I'm just interested on seeing whether you have two factors in these graphs and why not if you do not find and if you think that it's not possible. Which of the following graphs have two factors? Can you find two factors here? What is a two factor? A two factor is a two regular spanning subgraph, meaning, of course, you must cover all the vertices and if you say two factor, then the edges must form cycles, disjoint cycles. Okay, a two factor is just a subgraph made of disjoint cycles and taking in all vertices. Okay, I can see many two factors here. I can factor this, for instance, I draw now in some two factors with different colors. This is an easy one, but this is another one. Okay, and of course, this is another one. Okay. There is also another one, which is just made of one single cycle, which is this. No, sorry. Okay, so this is the idea of two cycles. And so the question is, so now we have seen that this one, the 3 cube, actually has two factors. I tell you, no, I don't tell you. Try to ask for yourself. Does this have two factors? Does this have two factors? If there is one, find it, show it. If you don't find any, do you think that none exists? If you think that none exists, can you prove that no two factor exists here, no two factor exists here? Okay, all right. And these are the problems you are left with. And don't forget the other problem. Try to find a Eulerian graph which has an odd number of edges and an even number of vertices, or prove that no such a graph can exist. Okay, it is just one of the, I think maybe the only problem I've given in the chapter Euler, Tools and Hamilton cycles. So you find it in the list in the program. All these exercises are listed, and so you find it, okay? All right. Are there any? No, I have 5 minutes just to give the initial. Oh yeah. Okay, we have edge colorings before. I like very much the chapter on independent sets, but let's look at the beginning of this chapter. We have a loopless graph G. A K-edge coloring is an assignment of K colors to the edges of G. The coloring is proper if no two adjacent edges have the same color. Okay, this is what we are interested in. Proper colorings, meaning that we give colors so that no two adjacent edges with a common vertex share the same color. But you can also think of the K-edge coloring as a partition of the set of edges. Where, okay, in the set of edges colored by color 1, the one colored by color 2, up to the ones with color K. What do you do when you do this partition is that you must have that each of these sets must be a matching, okay? Because the ones colored with color 1 must not have a common vertex. The ones with color 2 must not have a common vertex, and so on and so forth, okay? G is K-edge colorable if G has a proper K-edge coloring. And if you have, again, this is, the next thing is what a mathematician says. How many colors are necessary, or how many are sufficient? Oh, one for each edge. Okay, if you take as many colors as there are edges, you're pretty sure that you can color your graph in a proper way so that no two edges are colored in the same way if they share a common vertex. Okay, I give just one different color to each edge. Of course, this is the mathematician's answer, but the engineer's answer is, okay, but who cares for such a silly solution? What I want is to use the smallest possible number of colors, okay? And so, of course, it is epsilon edge colorable, every loopless graph. Oh yes, if you have a loop, then nothing is possible, because a loop shares a vertex with itself, and so if you have a loop, you cannot properly color the graph. So here we always talk about loopless graphs, okay? If G is K-edge colorable, if you can color properly with K colors, then you can also use more than K colors, okay? And we are here with the Edge-chromatic number. He, this is Greek letter he prime of G, which is the minimum K for which G is K-edge colorable. And G is K-edge chromatic if he prime of G equals exactly K, okay? Why he prime, and where is he without prime? Later on, because he is reserved for the same problem, but for vertices, okay? Okay, I'll stop here. We'll start back with these things next Monday, but here I'll go a little bit quicker and we'll start thinking how many do we need as least as few as possible. Okay, always this type of ideas. How can I have a big matching? How can I have a small covering? How can I have a small number of colors for the edges? And in two chapters, how few colors can I have for vertices and so on. Okay, this is the leitmotif in graph theory. Okay, see you next Monday. Ciao.
Have a good night, sir. Thank you.
Good night.